Welcome to Module 46 on correlation and regression. Whenever we are dealing with any kind of empirical exercise between any two sets of variables between x and y, we are interested to find out any degree of association between them. And this degree of association is formally called correlation. So by correlation, we raise a question, is there a relationship between the two variables? Because it is done in a bivariate framework where we take two variables are affecting each other. This is providing us a kind of confirmation where we can go for any kind of functional relationship. So in a functional relationship, the dependent variable is affected by the independent variables that requires to be estimated, and this calls for regression. So from the very beginning, it is very important to understand the correlation and the regression exercises which are basically intertuned with each other. Moreover, in a data analysis, another important methodology crops up which calls for causation. So by causation, we means two-way relationship among the variables. For example, in empirical studies in economics, we deal with a kind of a study between FDI and economic growth. In most of the studies have actually raised the issue of causality between them. That means a good performing nation will be attracting more and more capital flows, whereas also FDI will stimulate growth by itself. So if there is a kind of two-way relationship between x and y where we can stipulate one to be dependent and one to be independent, then we go for causation. So actually we can say that correlation basically depends on the degree of association. Regression is basically a step to confirm the degree of correlation. And finally we can make out that the correlation and causation are not the same, because causation is basically about the two-way relationship that comes in force. This boils down to look into the two specific questions. Firstly, what is correlation? So by correlation, we mean the degree of association which needs to be estimated, and the association between the variables is the most important thing, which can be captured graphically and also can be computed mathematically. This boils down to the most important graphical representation of getting the correlation, which is formally called scatter diagrams. So these scatter diagrams are basically the plots for the two variables y and x which are affecting each other. So if we refer to the first point on the positive correlation, then we find out that the pattern of the scatters follow an increasing trend. That means the patterns that we observe, that x and y are directly related to each other, and that is evident from the positive correlation. But when we go for the negative correlation, then x and y are inversely related to each other. That means with the rise in y, x falls, or vice versa. And that also is being depicted by the negative trend between x and y, or negative correlation as we can say. Further, when we discuss on no correlation, it means that neither positive nor negative, so circular flow comes in, and this calls for no correlation. So that means in any one of the scatter diagrams, we can be rest assured that by the patterns we can make out whether x and y have an increasing trend, whether x and y are inversely related to each other, or whether they are not having any kind of relationship between them. And that is evident from the scatter plots as we can see. So the question arises that how can we take care of the correlation? So to get into the correlation concept, first of all, we need to understand that two variables are changing together. And in order to capture that, we concentrate on two terms which are used in statistics. One is variance, another one is covariance. So variance basically leads on variability of the single variable and the deviation from the mean. So the square of the observations from the mean will be capturing the variance, and whenever we are going for the covariance, it is the degree of association between them, that is xi deviation from x bar, yi deviation for y bar, and that is how the degree of association can be done. So covariance is actually a tool which calls for both movements of x and y, and that can be captured. This boils down to a very important expression of covariance between x and y. By this expression we mean that the covariance between x and y is basically given by summation of I running from 1 to n. So I is the level of the observations of the sample which runs from 1 to n. Xi and yi are the specific observations. Deviations are taken from their respective means x bar and y bar, and thereby the denominator is considered as n minus 1, but in the numerator we have xi minus x bar and yi minus y bar. So we can observe that if x and y both are on the rise, that means we have an increasing pattern, then the covariance will be obviously positive. But if we find out that x and y are inversely related, then the covariance will be negative. Otherwise, when x and y doesn't have any relationship, covariance will be 0, and that is being done when no pattern is coming up. So basically the covariance expression tells us very clearly that xi minus x bar and yi minus y bar can be summed up over n observations, followed by a kind of an increasing pattern or a decreasing pattern. But if there is no relationship, then the numerator becomes 0 or the covariance becomes 0. This is how we can see with an example or with a tabular representation. So here two types of data are considered. A data where there is a high variance, that means here the variability is more, and the second set of data where the variability is less. So we have the 7 important observations, 1 to 7. We have the data on x and y, and accordingly we have the mean of x and y. Moreover, we can see that the covariance is calculated as 1166.67, which appears to be quite high comparatively to the low variance data, which is very low. That means depending on them we can make out the variability of the series and about their deviations from their respective means. This also boils down to one of the important solutions, that how can we go for correlation coefficient. Because to arrive at the correlation coefficient, our most important component will be covariance in the numerator and variance in the denominator, and that will make us very clear to find out the degree of association. So in this particular correlation, we are going for Pearson correlation coefficient. And that means that covariance does not really tell us anything, it is just a standardization. But actually when we go for a Pearson coefficient, it standardizes the value, and that is what it divides the covariance by the product of the standard deviations of x and y. So only by studying covariance we cannot make out about the degree of the correlation. But once we divide it by respective standard deviations, we can get that. And that boils down to the most important expression of finding out the correlation coefficient. So here we observe small r as the degree of the correlation coefficient, xy in the suffix shows the dependent and the independent variables, or the two variables which are taken up in a bivariate framework. The numerator shows the covariance between x and y, and the denominator the respective standard deviations of x and y. So that is how the correlation coefficient can be coming up. In this particular context, we can see that the covariance has the variance or the deviations from mean in the numerator, and n-1 appears in the denominator. This n-1 is basically the degrees of freedom, which boils down to the correlation coefficient Rxy. And finally, we can explain that it is basically the Zx. So whenever I am finding out Zx1, it is basically making each observation deviation from its mean x bar, and Zy1 is observation of yi from its respective mean y bar, and thereafter the correlation coefficient of Rxy comes in place. So this is basically in accordance with the Karl-Pearson correlation coefficient. However, there are certain limitations of using correlation coefficient. The limitations thereby explain when we take out the extreme values of r, because this correlation coefficient can lie between -1 and +1. So if we consider r equals to 1, that means all the independent variables are basically actually predicting the dependent variables with absolute certainty. That means there is no non-stochastic factors or no random factors are there, so that x and y are explaining both of them in full order. So all the data points are on a straight line and we get a linear equation. So this linearity comes up in place when r equals to 1 or minus 1. Why? Because it can be a positive straight line or it can be a downward sloping straight line. In either of them, y and x are completely explaining each other. Secondly, r is also actually the true of the whole population. Because you have a total population and r can explain on that, and also we can estimate r on the data. So that means the correlation coefficient is also affected by the variance, and variance is largely affected by the extreme observations. So that means we can say that this r is very much sensitive to the extreme values, which we say outlier in the field of statistics. So basically when we talk about the limitations of the correlation coefficient, either we predict x and y fully, or we know the actual r and how the estimate of r can be done. But on the other hand, r is very much sensitive to the extreme observations that are taken in place. So this boils down to the very important confirmation that we get as regression. So whenever we are satisfied with the correlation result and we get a kind of a pattern, either the variables are directly proportional or the variables are inversely proportional, it gives us the confidence to go for a estimation exercise. And this estimation exercise is none other than regression. So regression is the next step which comes after the correlation. So by correlation we mean there is an association between x and y, but it does not explain what is the factor of y explained by x in terms of proportions, in terms of percentage. And that is how the regression comes in place. So for this we concentrate on the word regression. So when we are dealing with the word regression, we are referring to a linear setup or a linear data such that y hat equals to ax plus b. That means we are basically going for fitting the baseline so that x and y can be better fit or can have a satisfactory goodness of fit, or x can completely affect y. And this is what comes in a regression exercise or in a regression line. This also takes care of minimizing of the distance. For example, we see y hat equals to ax plus b, where a is the slope and b is the intercept. So here we have an upward sloping line or an upward trend. And these are basically the exact observations. So we find out the distance of this particular point from this straight line curve, which is the best fitted line we say, and this distance needs to be minimized. And that is how we can go for the residual error. So whenever we are going for a residual error, we are finding out the difference between the actual value and the predicted value on the straight line, and that is how the residual error comes in and the best fitted line comes in. This also takes care of the most important methodology that we are used to, and that is none other than least square regression. So in any kind of correlation exercise, as we go for estimation of a functional form or estimation of a particular relation, we want to minimize the errors. So errors are basically the distance of the actual observation from the best fitted line, and this calls for least square regression. So under least square regression, we minimize the sum of the squares of the residuals through a kind of a model line which goes for y hat equals to ax plus b, and a residual component comes in which is actual observation minus the observed or the predicted observation. So this can be positive or negative, and we sum up the squares of the residuals. So once we plot the residual series and we do the squaring off, then we can be able to minimize. So this square of the residuals needs to be minimized such that we can get a proper estimate of these unknown coefficients a and b. And that is how the least squares regression comes in place. So that is how we find out the value of the slope coefficient, which is the point b. So in this particular exercise, we can say that the value of b actually looks for minimizing of the sum of squares, where in all the three cases we have three different observations. First, we concentrate on this particular case, which is this particular scatter plot, where we find out that this fitted line passes through the origin. So when it passes through the origin, it means that it has no intercept, and the line is basically having the only slope which is positive, and we can find out this error or epsilon, which is the distance of the plot from the straight line. Secondly, we go for any kind of fitted line which is above the origin. So when we go for above the origin, then we can find out that it is intersecting on the negative axis or on the positive axis, and thereby we can get the value of the intercept and by default the value of the slope. Secondly, we find out that B is also coming up when we are shifting the line a bit upward. So actually we are trying out different values of B, and which can be done by shifting the line up and down so that we can get the better fit and we can find out the slope of the estimated equation. So this is very much in tune with minimizing the sum of squares or minimizing the sum of residuals. Now we get the value of A or the intercept that will minimize the sum of squares. So in this particular discussion, as we see in the three cases, A can be 0 or A can have a positive or a particular negative value. So in all these exercises, the most important technique that is applied is basically minimizing the sum of squares. So when we minimize the sum of squares, we say need to minimize summation y minus y bar whole square, where this y hat is the predicted value of y, which comes out as ax plus b. So it is necessary to minimize this expression, and once we plot the values, we are getting the minimum point where the values of a and b can be determined, because that is the error which is to be minimized. So in this particular methodology, we are basically arriving at some kind of consensus regarding the application of mathematics. So what is that? The minimum sum of squares is at the bottom of the curve where the gradient is 0. So on the basis of that, we get the value b, and that is by taking the partial derivatives with respect to a and b. So we solve for all of them and the values, and thereby we get the final result. So in this particular expression, we see that the following equations come in, where we find that the standard deviation of y divided by the standard deviation of x comes in, followed by the correlation coefficient. So whenever the correlation coefficient appears to be low, then the slope is said to be flatter. Moreover, whenever we are referring to the spread of the y, then high standard deviation comes in, and whenever the spread of the x, then we have a high standard deviation in terms of x. So in both the cases, we can see that the variability can be easily managed or can be taken care of. So in this particular model, we continue by saying that y hat equals to ax plus b, which is our model equation. And then when we say that the line will pass through mean, so we go for the mean of y, which is y bar, which is equal to ax bar plus b, and from there we can find out the value of the intercept, which is y bar minus ax. This is what we put up in the equation, and we get b, which comes up as the expression for the slope, where y bar minus r sy by sx. This sy is the standard deviation of y, and sx is the standard deviation of x into x bar. So what we observe is that smaller the correlation, closer the intercept to the mean of y. So that is how the correlation and the error can be interrelated. This boils down to back to the model whenever we are explaining this entire dynamics using a kind of a flow diagram. So first of all, we are referring to this equation y hat equals to ax plus b, which is the predicted value of the y, and that is estimated. A is said to be the slope, x is the independent variable, and b is the dependent variable, or we can say the intercept term in this case. So we observe that r sy by sx can be considered in place of a, which comes up as one of the most important expression for intercept, plus y bar, which is also coming up as the mean of y, minus r, which is the correlation coefficient, standard deviation of y divided by standard deviation of x multiplied by x bar. So the entire thing rearranges to y hat equals to this coefficient which comes up under the correlation coefficient into x minus x bar, that is the deviation from the mean of x plus y bar. So if the correlation is 0, we will simply predict the mean of y for every value of x, and our regression will be a flat straight line. So whenever our regression will be a flat straight line, definitely the correlation happens to be 0. But also we have to understand that for every case it will not be useful, because we can calculate the regression line for any data, but the important question is how well the data is fitted. That means whether the observations are too far from the line, then the fit is not good, or the observations are near to the line, then the fit is good. So that is how good is our model, that is questioning on the goodness of fit. And in order to do that, we go for the standard deviation of y, which explains sum of squares in the numerator divided by the degrees of freedom, which is df, number of observations, minus the variable to be estimated. Then we have the variance of the predicted values, that comes up as standard deviation of y. And finally, we have the error variance that comes in. So in all the three cases, we can say that the variance of y, the error variance, and the variance of the predicted values are interconnected with each other, and that speaks about the goodness of fit of the model. And we can continue our discussion in this way by giving a kind of an expression where we say total variance, which happens to be predicted variance based on the y hat, and then we have the error variance. So whenever we go for the error variance, it means the variance that has been originated from the random term or the error term. And that is how we can say that from the cross multiplication by rearranging, we get a very important expression, which is r square, where the standard deviation of y divided by the y. That means y hat is the predicted divided by the y, and that is the proportion of variance in y explained by our regression model. So what proportion of y will be explained by a regression model, that is already implied in the error term. And that is how we can see in this following expression when we substitute. So in this following expression, we can see that your SER square, which means that an error term of the variance or the variance of the error term, is related to the R square. So if the R square is 0, then definitely the entire error is explaining the change in the dependent variable y. And as long as r square is less than 1, then definitely the error is partially affected by the independent variable or by the other factors. So greater the correlation, smaller the error variance, and better our prediction. So if the correlation is on the high, definitely the error variance will be on the less, and that will make the result to be more consistent. So this boils down to how the model appears to be significant. So in order to do this, we go for a testing exercise, which is F statistic, and we find out whether the model has an overall goodness of fit, whether we are accepting the null hypothesis or the alternative hypothesis. And this finally comes to the concluding remarks on this particular module regarding a general linear model or a linear regression, where we have one independent variable and that can have a straight line, and also it can be extended to multiple regression where there can be more than one independent variables. So in both of the cases, we look at the goodness of fit. In both of the cases, we talk about the error variance, and finally we judge on the best fitted line. So that is what the most important contribution of correlation and regression taken together. Correlation studies on the degree of the association, but the regression makes the estimation to be perfect, or whether a good fit can come up from any estimated relationship. And that is how they are interconnected. Thank you.